So now that we've talked about the common fork join pool's implementation, let's talk about how you can configure different elements of the common fork join pool, and we'll also sort of motivate why you would want to configure elements of the common fork join pool. By default, the common fork join pool has one less thread than the total number of cores that are known to the Java execution environment. So for example, if we were to run this little program, as we do here, and we called ForkJoinPool.getCommonPoolParallelism, if we were on a quad-core processor, we would get the value 3 back, because there's always one less than the total number of cores. Why is that? The reason for that is that the calling thread, the thread that sets the stream in motion, is basically borrowed by the parallel streams framework in order to be able to pitch in and do processing as well. So the 3 threads that are part of the common fork join pool plus the calling thread together will process the stream. So therefore, if you have n cores, you'll have n threads running, but the common fork join pool will only have n minus 1 threads. Now, the problem arises here if the default number of threads in the fork join pool are inadequate. And there are some situations when that can occur. What might those be, you might ask? Well, let's take a look at a parallel processing program like this one, the image stream gang program, that is going to deal with a bunch of images. And just for sake of argument, just for kicks, let's say that we've got more images than we do threads and cores. So let's say we have 10 images we want to download. We've got 4 cores, so we'll have 4 threads. Why would that be a problem? Well, the problem will occur if we're trying to download more threads. And the typical issue here really is that you're going to underutilize the processor cores. And why would you do that? You would underutilize the processor cores because whenever a thread goes to download an image, it could take a while to download it. And as a consequence, during that time, that thread will block waiting for the I/O to complete. So this works both for input, for reading, for example, from a socket from a web server. And it could also occur for your writing. If you're going to write a large image or a large document or whatever to the file system locally, that takes time. And so when that happens, that thread goes to sleep. Now, if you've got only 4 threads but 10 things to download, an awful lot of time of the program will be blocked waiting for I/O to complete when there could be other things going on. What would those other things be? You could be downloading or attempting to download the other 6 images in other threads that are going to perhaps block as well, but what the heck, we can have them all block, and as those threads complete, the work will get taken off, and you can at least start the downloads in parallel. So the thing to remember is that when one thread blocks on I/O, that doesn't mean nothing else can be done. It means that we need to get another thread to do something else, which could also be trying to do downloading things in parallel. So what we really want is we really want to have as many threads in the common fork join pool or available to the overall program as there are blocking operations. So if we have 10 blocking operations, we want really 10 threads in order to make sure that we're maximizing processor utilization, processor core utilization. There's some other subtle problems here having to do with deadlock. We're not going to talk about those right now. But the main problem is underutilization of processor cores. So how do we solve this problem? Well, there's a couple ways to do it. One way, if you happen to know ahead of time the total number of images or blocking operations that you're going to want to work with, then you can tell the common fork join pool at startup time, this is the size the pool should have. And you can do that by using the system.setProperty method, and you pass in this crazy string that says java.util.concurrent.forkjoinpool.common.parallelism, and you can give it a flag that says how many threads you want. In this case, we could give it 8 threads or 10 threads or whatever. And in that case, it would end up with that many threads created when the common fork join pool is first started. But there are really 2 problems here. One of the biggest obvious problems is that sometimes it's hard to estimate how many threads you need because you don't know until runtime how many blocking operations you'll have. So you could either set it too big or too low. And then the other thing is the way that the common fork join pool is initialized is this particular value is only used the first time the thread pool is created. And if you set it later than that, it's completely ignored. So you have to really make sure this thing goes early in your program before any use of the common fork join pool occurs. And the other problem is it affects all the other parallel streams in a process. So other parallel streams may not want to have it be bigger or smaller, and you've made them all be bigger or smaller. So there's these ripple effects that affect everything. Okay, the better way to do things is to use something called the managed blocker interface. And what that does, and we'll talk about this perhaps more later, but that's another topic again for a different class, is what it does is it will automatically and temporarily increase the number of threads that are part of the common fork join pool for roughly about as long as it takes for whatever bursty period of I/O threads or I/O tasks are required. So it'll expand the number of threads in the pool up to the number of blocking threads. And then after a little period of time, after those blocking threads are done, then the pool will shrink back down again to the default size, which again is number of cores minus 1. So it'll temporarily add these additional threads. And you can kind of think about this, if you want a metaphor, of something like Walmart or Amazon, where they hire seasonal workers during the holiday series, the winter holiday season, to expand the number of people there because they know they have more work to do. But they don't keep them around all year long. They hire them temporarily. This particular mechanism, the managed blocker mechanism, is very useful for tasks or behaviors that block on I/O or other synchronizers. What's interesting about this particular way of doing things is it can only be used, the ability to grow and shrink the number of threads in the common fork join pool is only useful with the common fork join pool. You can't use this with other fork join pools that are not the common fork join pool, because you can make your own fork join pool object and you can tell it how many threads you want it to have, and it'll do work stealing for you and so on, but it doesn't do the automatic growing and shrinking of the number of threads. Only the common fork join pool has that particular feature. So that's the end of the discussion of configuring the common fork join pool. We will take a look next time at a couple little programs that demonstrate the virtues of being able to configure the common fork join pool, and that'll give you a better feeling for why you might want to consider doing this stuff in practice. It's actually not a very hard thing to do this, but it requires knowledge of a few features that are not well known, so you now have deeper insight than the average person would have about how to control the size of the number of threads running in the common fork join pool.